So these are all of them?
There should be three of them. First one is just
So I'm uploading them to my account. So we can run it from there. What item is an upload?
no, there we go.
What's in RASC?
Yeah, the one I need to.
Yeah, what happened to
Hello, folks online. If somebody can just validate that you can actually hear me in the chat.
Oh, I got it. What's
Hi,
you?
Dennis. Yeah, we can hear you.
We have a little bit of some communications issues here. So we're getting set up there. We'll just be a couple of minutes here. And then we'll get started. You want to go ahead and get Gail's presentation? Yeah, just put- Places. You can just put places.
Oh,
Buy stuff for him, so he doesn't buy good health. You just get
That's Chris, do we have some volume?
Yes, there we go. All right, folks, we're just about ready to get started here. Just getting the presentation up. Now we got the presentation. We're gonna start a slideshow.
We still need to connect the microphone. We're zooming this.
We're feeding it through my computer here, so I'm.
Okay.
what they can't see anything
They will in a second. I'll,
unless you point it over.
that's what I intend to do, but it's not very good.
But I think we can get both somehow. Nope, okay, I'm not gonna jinx it.
What we can do is turn the lights down. That's over here. There we go. Now you can start seeing it. It's gonna be weird. All right, folks, good evening. And welcome to the RASC Winnipeg Centre's annual monthly meeting and our quarterly IT issue. As we work through that, as you can see, adapt and overcome. A little bit of background here. My name is Dennis Lyons. I'm the president. Just want to welcome all those that are online. And for those that are here in person, thank you very much for coming. I'm just going to start off the meeting with our land acknowledgement. The lands from which our members and guests are joining us are located on the original lands of Anishinaabe, Cree, Ojibwe Cree, Dakota, and Dene peoples, and on the homeland of the Métis Nation. We respect the treaties that were made on these territories. We acknowledge the harms and mistakes of the past, and we dedicate ourselves to move forward in partnership with Indigenous communities in a spirit of reconciliation and collaboration. So welcome, everybody. I'd like to welcome our first guest speaker tonight, gAIL Wise. gAIL Wise, come on up.
Oh, it'll work. Guaranteed it'll work.
Yeah, you should really move it out. Yes, back.
We can turn the lights way down. I've got a light here.
How much cord do you have?
Well, it's more, we're connected, not much because we're connected. But it's not the power in it. It's within the camera.
Years old. This is my old Capson now, and this was her favorite object. The ancient Babylonians, Turks, Persians, Egyptians, Romans, and Greeks all saw fish in this group of stars. The ancient Middle East had their rainy season when the sun was in Pisces. And so this area of the sky surrounding it is known as the waters. It contains a dolphin, a seagull, a river, a water carrier, a sea monster, and a fish. Pisces is the 14th largest constellation that these track, and it covers an area of 889 square meters. These thoroughly unrecognizable fish in Pisces are swimming in opposite directions, and their tails are tied together. One fish is below Andromeda, and the other one is underneath the great square of things. Aries the ramps on the east, Aquarius the water is on the west, and directly south is the sea monster. The two fish are joined together in the seventh brightest star, and they form a skinny V pointing towards the sun. In Greek mythology, they were Aphrodite and her son Eros, and for the Romans, they were Venus and Cupid. One day, they were strolling along the banks of the river. Everyone was so huge that his head his top half of his legs were tin foil serpent, hissing snakes attached to his head instead of fingers. There were 100 serpents' heads, 51 hands. He had huge wings, and his beard was dirty and metal, and his eyes flashed fire. Typhon had come to terrorize the Olympians. To escape, Venus and Cupid got the idea that if they turned themselves into animals, Typhon might not notice them. So they went into the river when they went through, and they turned themselves into fish, which is kind of a strange idea for the gods of love and joy of the arrows. In another version, two fishes came to the rescue and carried 100 on their back. Anyway, they tied their two tails together as a golden cord so that they could never be separated. In Native American lore, Pisces represents a wolf. The wolf is a creature that doesn't think only of itself, but also of its seed. They are treated as amplifiers in their immediate vicinity, increasing the emotional intensity already present around them. Early Babylonians divided the constellation into two asterisks. The southwestern fish is known as the Great Swallow, or possibly Bucket. It is also known as the cord that ties the two fish together. The northern fish was called the Lady of the Heaven. The ancient Egyptians knew Pisces in the 18th village as the Queen of the Ocean. The symbol of Pisces, two fish, has been stamped down on the lid of the sarcophagus that we cannot more than 6,000 years. Pisces is a large pink constellation. Its brightest stars are only about 4th magnitude, but it is very important. It is one of the constellations of the zodiac, which I know means nothing to us, right? But the reason Pisces is so important is because it contains the Bryan equinox, which is the point in the sky where the sun crosses the celestial equator into the northern hemisphere. This happens every year, March 20th or 21st. In a word, springtime. It's also known as the first point of Aries, because about 2,000 years ago, this point was in the constellation Aries the Ram. But due to the precession of the equinoxes, it now occurs in the 14th. Astronomers use to spot the sun crosses at the first day of spring as the 0 point of the right. In very ancient times, Pisces was the Babylonian community, meaning the watery one, or more simply, the fish. In the beginning, the universe only consisted of a giant chaotic cosmic ocean, and that ocean itself was referred to as the universe. In some versions of this myth, at the beginning, of time, Mehet Weret was portrayed as a cow with the sun disk between her horns. Her name means great flood. She gives birth to the sun, said to have risen from the waters of creation, and it is said in some places that she has given birth to the sun of God. The universe was surrounded by a vast mass of primordial waters, and within them, a pyramid mound emerged from this primal chaos. There was a lotus flower within there, and when it blossomed from this emerged rock, there were many versions of the sun's birth, and it was said to have emerged directly from the mound or from the lotus flower that grew from the mound, in the form of a barren, a fallen, scarab, or a human child. In ancient Egypt, the creation was attributed to Athon, who is a deity closely associated with Ra. Athon was said to have existed in the waters of Nubia as an inner coherent being. Beginning with the middle kingdom of Egypt, Nun is described as the mother of the gods and father of the gods, and he is depicted on temple walls throughout the rest of ancient Egyptian mythologies. Nun did not have any temples or any center of worship. Even so, he was sometimes represented as a secret lake or an underground stream. It was also the Hebrew gAIL, or two fishes, and to the Arabians it was alpha, a fish. Pisces bright star, Qilak means four or five, and fish. So the translation is the core that ties the fish together. Its magnitude is 3.7, and it's 350 light years away from us. Eta also has the name Alfred, which comes from the star's traditional name, Alfred, meaning the spout or the outpouring of water. In China, Eta Piscium forms part of its asterism together with Rho, I, Omicron, and 104 Pisces. The asterism is known as the official in charge of the asteroid. Due to its position in this asteroid, Eta is known as the second star of the official party. There are a few significant characteristics of Eta. Its mass is between 3.5 and 4.5 times the sun's mass, and its temperature is 4930 Kelvin. So it's likely that the star's mass comes from the fact that it has deposited its hydrogen fuel and is now using helium in its core. Observations have revealed a rather mysterious companion of Eta, but nothing is known about this star except that it's separated from Eta by about 1 second of arc, which makes it very difficult to observe clearly. For instance, some observations show this star's magnitude 8, while other observations show it as Gemma's magnitude 11. What is certain is that the different magnitudes are the result of errors of observation and not because of variability of the companion. Since no orbital motion of the companion has been detected, it's likely that the second star is nothing more than a line of sight companion, although the two stars do appear to share a common proper motion. At our fish's southwest corner is its second brightest star, Alreshin. Its magnitude is 3.8, and its name is Arabic for because it knocks the thread that ties the two fish together. It was first observed to be a binary by Sir William Herschel in the year 1779. The stars are 1.8 arc minutes apart, and the period of revolution is 720 years. The stars are 150 light years away from us. South of the Great Square of Pegasus is the head of the western fish. This is an almost circular star known as the circlet. The circlet is an asterism, or a pattern of stars that is very easy to see in the sky. East of the circlet is the star 19 Pisces. This is a variable star that ranges from magnitude 5.5 to 6, which isn't a very big range. But what makes this star stand out is its very red color. This doesn't have a fancy name like the garnet star is the king, or the crimson star leads the hair, but you can see its red color naked eye. for sure. Near the westernmost border of Pisces is Gamma, the mountain of the western fish. This is the third brightest star, named from the Arabic for the fish's moon. Gamma, Theta, Iota, and Omega all form a jagged line that the ancient Chinese people call the gateway or lane. Gamma is magnitude 4.44 and it's 408 light years away from us. Gamma is moving across the sky 3/4 of a part second. Omega is a yellow-white dwarf star. It has a magnitude of 4.09 and it's approximately 106 light years away from us. This is the first star to the east of the circlet, so it's the first star in the fish's tail. Omega is suspected to be a close binary system. If it is a single star, it's 1.8 times more massive than the sun and 20 times more luminous. Iota is the eastern star in the circlet. Its magnitude is 4.22 and it's 44 light years away from us, which is very close to important stars. Its surface temperature is 6,000 degrees Kelvin, and it's suspected to be a very big star. It actually has 2 minor cyclic planets. Right on the ecliptic is Zeta, which is a beautiful double star of magnitudes 5.6 and 6.5, and they're separated by 23.5 arc seconds. It's 306 light years away from us. This was first recorded by Sir William Herschel in 1791. And it's shown virtually no change in the last 2 centuries. In Hindu sidereal astronomy, Zeta is identified as the first point of Aries, meaning when the sun crosses this star and the solar year begins. These 2 stars are very easy to separate in a telescope, and they have a distinct color contrast, yellow and pink. About 2 degrees south of Delta is a white dwarf star, which is of unusual interest. Its magnitude is 12.2, and it's one of the few white dwarfs that can be seen and identified in amateur telescopes. It was discovered by A. Van Manen in 1917, and it's known as Van Manen star. Except for the faint companions of Sirius and Procyon, this is probably the nearest white dwarf star to our solar system. The distance is only 13.8 light years. This is definitely one of the smallest stars known. It has a diameter of only 7,800 miles, or very close to the diameter of the Earth. It has a mass comparable to the Sun, so the density of this star is nearly 1 million times the density of water, or about 20 tons to the cubic inch. It has a relatively cool temperature of approximately 67 Kelvin. As white dwarfs cool with time, the star's temperature can be used to estimate its age, which is thought to be about 4 billion years. Pisces is home to a decent number of galaxies, but only one of them was big enough and bright enough for Charles Messier to include in his catalog. Right next to Eva is a large spiral galaxy, M74. This is the brightest galaxy in Pisces, and it's one of the most difficult estimate objects. It was discovered by Pierre Méchain in September 1780, and it was confirmed by Charles Messier in October 1780. M74 is also known as the Phantom Galaxy. Its magnitude is 9.44 and measures 9.89 by 9.33 arc. So it sounds like it should be big and bright, but since its magnitude is spread over its entire surface area, it really is very difficult to see. It appears as a faint circular globe with no details. M74 has 10 stars as known planets. John Herschel, when he made his general catalog in 1864, he made the mistake of classifying M74 as a globular star cluster, and this error was carried over into the MPC catalog. It wasn't until 1893 that it was identified as a spiral galaxy. M74 is one of the most perfect examples of a phase-on spiral. It has a prominent nucleus and well-defined spiral lines. Its distance is nearly 32 million light years from us, and it has a diameter of about 80,000 light years. Its luminosity is about 13 million times that of our sun, and it gives two clearly defined spiral arms and about 100 billion stars. 3 supernova are known to have taken place within M74, one in 2002, one in 2003, and one in 2013. And you can see that one as the bright spot just at the bottom left. Since that was the fifth one discovered that year, it's known as supernova 2013. It was as bright as 10th magnitude, so it should have been visible in just about any telescope in a good place. Another nice spiral galaxy is NGC 488. This one is seen face on, and it's almost as bright as M74. Its magnitude is 11.2, but it's much smaller. It measures only 3.5 Earth lengths, so it's really a lot easier to tell. This is a very compact spiral with very tight arms, so the light is more evenly distributed across its face. This one is also known as the Winnipeg Galaxy. The bright star in the picture is magnitude 10.2, so it looks bright here, but in the sky it really is not. There are a few other stars in this field. One of them is magnitude 7.5. So if you're a fan of star hopping, which I am, you should be able to find this one without too much trouble. Almost right in the center of the circlet is another spiral galaxy, NGC 7679. This one is magnitude 13.2, and it's only 1.2 by 0.8 arc lengths, so it's really easy. This one's about 200 million light years away from us, and it's 60,000 light years across. It was discovered by a German astronomer, Heinrich Ludwig Beres, on September 23rd, 1864. You know, I know about 10 people with birthday September 23rd, and I even had a couple of cats with that. Samantha on my first slide, she was a September 23rd. Right beside NBC 7679 is NBC 7682. The bright star in this image is magnitude 10, and the other ones are magnitudes 11 and 13. NGC 7682 is a barred spiral. Its magnitude is 14.25, and it measures only 1.15 by 1.07 arc lengths. It was discovered at the same time as NGC 7679, which is not too surprising. This one is 180 million light years away, and it measures 65,000 light years across. And these were the best pictures that I could find with these two. The rest of the ones I have are Hubble or gAIL, but I guess these are just that obscure. There are more than a dozen galaxies right inside the peak, inside about 2 arc lengths, but they're really, really small and really, really faint, like magnitudes 12 to 15. Just above that is a double galaxy, NGC 7619 and NGC 7626. These were both discovered by William Herschel on September 26, 1785. NGC 7619 is magnitude 11.4, and it measures 2.5 by 1.9 arc minutes. And 7626 is magnitude 12.75, and it measures 2.5 by 2.1 arc minutes. These are the largest of a small group in this area. So if these are the largest and brightest, let's see how small the others are. And you see 7611 is 1.7 by 0.8 arc minutes, magnitude 12.8. And you see 7693 is 1.3 by 0.95 arc minutes, the magnitude of 12.9. And NGC 7631 is 1.86 by 0.8 arc minutes, and magnitude 13.75. So I'm not even. Another pair of galaxies is NGC 470 and NGC 474. NGC 470 is a spiral, magnitude 11.75, and it measures 2.8 by 1.6 arc minutes. It was discovered by William Herschel in 1784. It weakly interacts with NGC 474, which is an elliptic galaxy. That one is magnitude 11.5 and only 2.6 by 2.4 arcings, 30.2 darkness. In the same field as NGC 467. These were discovered as well by William Herschel on October 8, 1785. Its magnitude is only 11.8 and it measures 1.66 by 1.5 arcings. Then we have NGC 520, which is also in the same field. This is a pair of colliding galaxies. This system is also known as the Lyons force. It measures 4.2 by 4.2 arcings, and its magnitude is 11.4, so you may have a better chance of finding this. Stellarium, everywhere I looked, said it measured 4.2 by 4.2, but I see it more elongated, so I don't know if you have it or understand. This system is 105 linear light years across, and it was also discovered by William Herschel on December 13, 1754. Right on the border of the Pisces and Cetus is NGC 128, at a magnitude of 11.8. This is a lenticular galaxy, which means that it's crossed between a spiral and a elliptic. This one measures 3.16 by 0.87 arcings, and it has an interesting shape as a box-shaped central mass, and it's been described as a peanut shape. I think it looks like a flying saucer itself. NGC 128 is the largest in a group of galaxies here, which includes NGC 125, 126, 127, and 130. And this alignment kind of makes me think of the alignment of M31 and 32 and 110. These are all magnitudes 14 and 15 and 8. So I really am not even going to find them. These were all discovered by William Herschel on December 25th, 1790. And that kind of makes me wonder what his wife was thinking if he was out hunting for galaxies instead of enjoying his Christmas dinner that she probably spent all day for him. There are even two meteor showers associated with our fish. One is the southern Pisces, which is active during the period of August 12 to September to October 7. The peak intensity is about 5 per hour, and it's from about September 11th to September 20th. And the northern Pisces, which goes from September 29th to October 12th, with a zenith hour period of 2, hardly what I would call a shower. Neptune right now is in Pisces. This is the stellarium chart for tonight. So this is something you can definitely look for that you should be able to find. So if you like small, faint galaxies that are impossible to find with an 8-inch dog, believe me, then Pisces is definitely the constellation for you.
All right, we're back on here for a second. Just get organized and then we'll start. Good. So again, thank you very much to gAIL Wise for the beginner session. So for the rest of our evening, we have the meeting welcome. I'm doing that. Talk a little bit about some few things coming up. Is that better? Then we have Bryan Stach for What's Up, What's New, Jayanne English, and then we'll have a break, and then we'll have our main speaker, Dr. Jayanne English, who will be talking about view, visualization, and the metamorphosis of galaxies. So just a reminder to everyone, we have our Lockhart Planetarium. If you're interested, they have events every month, and Danielle is the contact for that. Fundraising committee, Wayne Wong, Explore the Universe, Stan Runge. We also have our Telescope Loan Program, and Mike Brackus is the contact for them. We're still looking for some workshop ideas. Stan, we have the Stellarium workshops coming up. And that's being done by Zoom, correct?
Yes, by Zoom, correct.
Correct, there we go.
February 12th is the first.
And February 12th was the first one. The information went out to Minnecentrics and an email blast. So if you're interested, please sign up. And then there's more coming. Stan's got a bunch of them in the mix that they're working on. So thanks to Stan and his team for doing that. Our nominating committee this year is myself, Stan Runge, and Judy Anderson. We have an opening position of council president, vice president, treasurer, and councilors. The AGM is when those elections will happen. That's the 14th of March. During that time, we do the elections, the financials, and one of the reasons that it's moved out later in the year is just to allow more time for the financials to be completed and finalized, and for the audit committee to review them. Telescopes for kids. Wayne, did you want to speak? Oh, Wayne's sick tonight. There we go.
There's a GoFundMe page on the RASC website, for RASC Winnipeg website. And the main point of the holiday party is to get together next Saturday, but one of the aspects of that is there'll be some silent auctions and fundraising specifically for telescopes for kids. So maybe to say a little bit about what the program is.
Yeah, so Telescopes for Kids is a program where we will ask you to tell us a little bit about why you want telescope. And then we have a selection committee, and depending on how many telescopes and sometimes binoculars that we have, we'll determine how many people we're able to present scopes to after that. They also get a membership with the RASC for a year. So it's a great program. We've done it for a few years now. And again, for those that were online, Telescopes for Kids, there is a link to the fundraising page on the RASC Winnipeg website. So as well as the bank, potluck next week, we will be doing some fundraising there as well with silent auction and a few other little things. Just want to remind everybody, one of the things that's been changed at the National Council, traditionally there is, if you were a little slow in getting your membership paid up, there was usually a bit of a grace period, usually up to 2 months. Pretty much effective immediately, that's gone. So when your membership comes due, if you're not paying, the day it expires, you will no longer be a member of the RSC, and you'll have to renew your membership after that. They will be sending out renewal notices 2 months before and then 1 month before. So that's a recent change. We just want to pass that on to a lot of people. It's pretty easy to forget about your membership when we're doing it. I know I've done it in the past, so I can relate to this very much. So I just want to share that new information with the membership. So our February meeting, what we're hoping to do, or not hoping we're going to do, is we have a lot of members in the club who now use an e-telescope. We also have part of the loaner program, we have an e-telescope as well now. And we want to have a chance for those people to present their images. So we're asking anyone with e-telescopes if they'd like to put together a presentation, put together and to send it to the YouTube. send your images to Judy. And you'll be given the opportunity in the February meeting to come on up, talk about what you did, how long your exposures were, what your experience was with the telescope. Because this is really a new way of looking at imaging in the night sky. And it just be nice to share with others what your experiences are, good to bad. We've seen some people posted online and done quite a bit actually, showed them, but that's it. Telescope. So we just encourage you all, those that have it, to share your images with Judy, and she'll set you up for the next week.
Dennis,
Yeah,
if you could have the club's members will be here at the next meeting
okay,
as well, so people could see a little bit of what
there we
they're.
go. Yeah, that's good, thanks. So again, we mentioned about next week's potluck next Saturday. It's January 18th. It's at the launch co-working in the Exchange District, Suite 500, 167 Lombard Avenue, Winnipeg. Wayne assured us there's lots and lots of parking down there at that time of night, and so it should not be a problem. Just a reminder, it is a potluck, so bring what you like, and to be able to share. There will be an open bar. And as Judy already mentioned, it is a fundraiser for telescopes for kids. And if you know somebody who's got a slightly used telescope that you don't use, it might be appropriate for a beginner telescope, they'd like to donate it, that's always a good thing, to just bring that along as well. Or let people know when they can, how to reach out to the person who may have that scope. So that's great. Again, we have a GoFundMe page for fundraising towards this. And just quickly, our primary means of communication is on the groups.io site. This is some information on how to access it. Every person, when you first join the RASC Winnipeg Centre, you are uploaded to it. There's only, we limit how many we send out to every member. If it goes out to every member, it's usually something from the council. But then we have several subgroups where there's lots of different things. There's selling stuff, there's general discussion, as well as workshops, several areas. So that's our primary means of getting information into the membership of the RASC Winnipeg Centre. Members observing night is tomorrow night, 6 o'clock. Not sure what the weather forecast is going to be, but that's the time you scheduled for. That's when there will be a member up there to help you look at things and get settled up. So if you've not been out there, Jay was out there recently, the roads are good, everything's accessible, so it's not really a problem, other than dress for the weather, obviously. So what I'm gonna do is call out Bryan Stach to do his one-stop presentation. Shall you stay? Oh, okay.
So while we're waiting for the transition, did you know that the best place for a spy to hang out is on a satellite? That's because in space, nobody can hear you scheme. I have my sources.
All right, hi everyone, we're going to discuss what's up for January 2025 of this month. Something exciting is happening right now. I'll get into the details soon enough. Okay, so I'd like to talk about planets, but just to break it down, it's the only planets going to be visible in the morning. The rest of the planets that we have here are pretty much in the evening. It's happening right now, but I'm going to talk a little bit more about that. I'm a big fan of Mars, so we're going to catch up with Mars in just a few days. I'm going to greater details than that. The size of it is going to be 14.6. Other times it's been bigger, and other times it's been smaller. So we'll proceed on. Okay, for January events, doesn't look like there's much happening for it, but actually there's quite a bit. I'll go into greater detail again. Of course, that moon in Pleiades actually happened after midnight last night. I was talking to someone that actually it was pretty clouded last night. January the 12th is when Mars is going to get the closest approach. It's not going to be the absolute closest approach, but I'll discuss that in greater detail. January the 20th, we had Venus is going to be a few degrees north of the moon. And of course, the 21, the last quarter of the moon, and of course, we have the new moon on January 29th. Now, and that wasn't supposed to happen. That was supposed to call up every single time. So anyway, what's happening here, I'm supposed to call up each of these planets. These are the 6 planets that's happening right now. I'm trying to time this slide right here. And it's 7:52, and that was supposed to be roughly 7:44, but just kind of give you an idea of where the door is right now. And this is happening. We have 6 planet alignment right now. Of course, we have Mars, Jupiter, Uranus, Neptune, Saturn, and Venus. Of course, I don't have a laser pointer, but some of you probably recognize that we have Orion here. This was supposed to pop up individually, but it didn't work out this time. But anyways, so this is happening right now. So it's nice to have, we have 6 planetary alignment that's happening right now. Of course, over here, you'll see here Saturn and Venus is going to be quite close with most of the part of the month. What's happening is Venus is going to get a little closer here, and then it's going to move up. Okay, so okay, so Mars, as I mentioned before, on January 12th, this is the closest approach it's going to get. It's not going to be the absolute closest. Other times it's been closer. Occurs with the magnitude of 1.3 minus 1.3. With the magnitude with the size of 14.6 arcs across. Now, this is a retrograde motion will take place after January 12th, but it's that's the closest approach. Okay, so in this simulation, hopefully this is going to work for me, and it didn't. I'm reading. It's a wonderful night. Yeah, this is really good. Okay, what's happening here right now? What I'm trying to find is, of course, we're a little faster than Mars. Okay, so what I'm trying to explain here is we're catching up to Mars, and January 12th pause right there. We catch up to Mars being the closest approach at that particular instant. And then what's going to happen next is that we're going to speed up a little bit. So the next 2 years from now, we'll catch up with Mars again, but the size is going to be what, 13.8 across. So, and then after that, what's going to happen is, as you can see here in this chart here, when I try to explain, okay, so at 2027, it's going to be 13.8 across, and then what's going to happen 2 years after that, 2029, then it's going to go back up it takes every 2 years for us to catch up with Mars. So, and again, it's not always the same thing. One thing I really liked back in 2018 when I tried to do a Mars kind of event at Planet B, it was July. It was nice and warm. I wish it happens all the time, but as you can see here, it's not always. Sometimes happens during the months, but that's how it works out. Okay, so as I mentioned here, now Venus is going to be about 3 degrees north of Saturn here. This is not really good reputation for it, but Venus here is a little bit brighter than Saturn, as you can notice here. Just going to be 3 degrees north of Saturn. But now when I looked at Saturn, it didn't work this time. The rain started just only about 8 degrees off. Unfortunately, it'll take another year for the rays to tilt a little bit more, and then another year after that to get to the tilt that we'll like to see. So tilt is, it was almost edge on just a month ago or something like that. So anyways, we had a little bit something with tilt. Now this is something that, I just kind of came across accidentally. One of our members, Stan, is really big on the crescent moon, so I try and catch the crescent moon, but this month it's happening really good. Meaning that it's just, you can't really see it, it's a thin crescent moon. This is happening on January 31st. But it happens early in the evening, just after just sunset right now. And I'm gonna try to blow it up here. As you can see, it's a thin crescent moon. It's gonna happen most of the evening. So I think that's quite nice. Hopefully it's going to be a little warmer there, but I'll explain a little bit more about what's going on with the weather. Of course, here, in this example here, and you can see here it dips quite low here. Temperature, if you notice, the trend is it gets really cold, it gets really warm. So this weekend, unfortunately, it is going to be about 80% clouds, but we are calling for more snow in the forecast. As you can see here, this little graph right here, it's accumulated snow here, and it looks like again more snow. As you can see over here, this graph here, which I'll laser pointer. You see here, it's so there's a Qilak coverage right here about 100%, so it'll be at 80% for the better part of the weekend. So fortunately, not this weekend, it's gonna really work out, but then again, who knows, tomorrow it could all change again. But anyways, that's all I have to say for what's up for January 2025. Thank you.
Thanks, Brian. And we'll just call Jay Anderson up. Show us. Let's do.
Okay, here we are, coldest month of the year. Another 2 weeks before we get what is typically the coldest day of the year. However, I've got to look at the long range forecast and for the next year, and it will be above and freezing the whole time, and the skies will be clear all the time. And I feel because the money crunch is going to shut off all the city street lights 10 minutes after it pops out. And then we might be able to see some of this stuff. I want to talk about Jupiter's clouds. There's some interesting things that have been worked on there. A small paper, but I like this because this is a study that involved amateur astronomers. And these two pictures were taken by Mike Baracus. Some of you have seen them on the thread already. The one on the left was taken 2 nights ago, and the one on the right was taken last night. Much better seeing, and you can actually see Ganymede, I guess, the moon that's off the top shoulder of Jupiter, and the shadow of Io on Jupiter, and above Io in the middle of the red belt in the northern hemisphere. You can see Io itself, it's a casting shadow. Mike is in Curacao, where Jupiter is straight overhead, and the temperatures are above zero all the time. And it's not quite sunny all the time, but it seems to be good enough for his purposes. What's happening? Here's a diagram of the temperature structure of Jupiter's atmosphere. It's mostly hydrogen and helium. There's a lot of other stuff in there as well, and including some complex organic compounds that are probably responsible for a lot of the colors that we see in Jupiter's atmosphere, Jupiter's cloud band.
But do you see that, this, temperature profile you see here was taken by the Galileo spacecraft when it dropped a sensor, a little satellite into the atmosphere. And, so starting at 1,000 kilometers up, you've got very, very warm temperatures, and they cool off until you get to 320 kilometer level there, second dash line from the top. You get into the stratosphere. This structure is very similar to the Earth's atmosphere until you get down to the tropopause. Now, a little red arrow there is approximately what the surface pressure is on the Earth. So 50 kilometers high from the quote surface of Jupiter, because this level is generally selected as the base level of the atmosphere. So there you get a tropopause and the cooling or almost equal temperatures all through the stratosphere start to warm up again. You can see that there are three colored bands there, which are cloud bands that were sort of detected by the Galileo spacecraft. The problem with Galileo is it was meant to drop into the middle of a very sort of active cloud band, and instead it dropped into the middle of essentially a high pressure area where there was almost nothing happening. So its detection of clouds was somewhat fuzzy along the way. You can see they've got down to 132 kilometers underneath the our sort of base level, and that's when it stopped transmitting. It doesn't look like very far, but in fact, it was at about 15 times the surface pressure of the Earth at that level, and it finally was transmitting. In Jupiter itself, the white zones are commonly thought to be ammonia clouds, and the darker belts see on the images are the belts are sort of unknown composition, lots of different chemistry going on. So what happened is that group of astronomers, including amateur astronomers in Arizona, decided, or in Wyoming, decided that they would get together and contribute to a study of what the ammonia clouds are like, how they vary spatially. Instead of looking at all of the types of clouds, just want to look at the ammonia. I've got a cloud derived from ammonia and condensation of ammonia. And so what you do is you look at the planet in several different filters, and it's fairly common to have a methane filter to look at Jupiter and at Saturn. Mike has his own observations in that band. But if you pay for other filters, you can look at other wavelengths that are showing an emission from the different species, in this case ammonia and methane. And so on the left here, top two images on the left, we just see white light pictures of Jupiter. And then in the middle, we see so that pictures through the different filters. On the top, you see the transmission through the methane filter, and in the middle there, you see the transmission through the ammonia filter. There's a little bit of a problem on the left edge of that because of the timing area of Jupiter rotated into view where they've been had nothing just to reconstruct that. But anyway, you just invert those two images, at the old invert scale on their display, and you get what's called the opacity. That is how much these different molecules block the light in a sense. And so when you have the opacity information, and you have to remember that each one of the pixels in this image is a numerical value that tells you what the opacity is. So you can manipulate them mathematically. And so you can take this stuff into a model and use that to model the amount of ammonia. Now, in this particular study, they also had backup from some of the world's biggest telescopes, because it was partly a test to see how well a C8, an 11-inch electron, which some of the foam could actually be used to map ammonia in the atmospheres of the large planets. use a ratio of the numerical value of methane to ammonia. Because the NH3 molecule is largely constant, it doesn't change. So what you're doing is looking at the amount of ammonia in relation to the amount of methane in the atmosphere. And from that information, you can derive a lot more information about what the surface pressure is at the level of the cloud tops. You can derive the temperatures at the top of the cloud and a number of other information. So here you see a graph that sort of, you can see the bands here. All of the bands except the dashed one that peaks way up high are taken through, it says SCT on the graph, that's for Schmidt-Cassegrain telescope. And so all of these lines taken at different times, 2020, 2021, 22, are showing, if you took a line straight down through the middle temperature from north to south, how much ammonia you had in each one of these at each point along that transit. And so you can actually see which bands in Jupiter have lots of ammonia, which have minimal amounts. The dashed line is the one taken by the very large telescope in Chile, and it goes to show that what the amateurs are able to collect is actually very similar to what 8-meter telescopes sitting at 10,000 feet in Chile would do. The importance of this is not the detection of this, because you don't need amateurs to tell you where ammonia is in Jupiter. But those big telescopes can't monitor Jupiter all the time. And so what you do is you get a collection of amateurs who will take these images using the standard techniques they're always doing, as long as they've got the filters, and then they can amass this information and watch the variation of the ammonia cloud in Jupiter over a period of time. Something that just can't be done with big telescopes because the demand on their time is so great. So what did they come out of it? Well, the main problem they had is that they detected that the ammonia ice condensation was at a much higher pressure level than they thought. And so the clouds that they thought were ammonia in that Galileo transect or sampling, in fact, couldn't be, because it's actually too cold at that level, or too warm rather, and the ammonia would not have condensed. They did also the same thing on Saturn. I haven't presented any results here, but it's a similar chemistry in the atmosphere that requires a little bit more exposure. The solution there is what's in yellow on the bottom, quoted directly out of the paper that came out of this. And it shows that, once again, last time I showed you something that amateur astronomers could contribute in. And so again, here's another project that can benefit from the same thing, as long as you've got $10,000 with telescope filters. It sounds funny to say that, but there are more than a few people than this well to do. This is a really interesting thing. You know, the James Webb Space Telescope spends a lot of time looking at stuff. And while they might be photographing one thing, there's a lot of other stuff that sort of passes through these images that they take. And in this case, they're monitoring the TRAPPIST-1 planetary system. And what they do with that is they basically stare at it for almost 94 hours. And the difference is when you're looking at that star, you're looking for dips in brightness as the actual planets go in front of them. And there are quite a few exoplanets in the TRAPPIST-1 system. But while you're looking at that star, which in the image, the big image on the left in here, the star is in the center, but other stuff goes through the field. And on the left underneath the yellow arrow are two previously known asteroids that are drifting through the field. But then there are 3 dashed lines in various colors because there are different wavelengths. And these represent unknown asteroids that passed through the field while they were studying TRAPPIST-1. And they're broken up because there's a series of separate short exposures that are made, and every time there's a gap in time between the exposures, and the satellite doesn't show up. And in fact, in those 94 hours of observing TRAPPIST-1, they detected 138 unknown asteroids passing through the field of view. And because these were unknown, and because it took the James Webb Telescope to see them, they're actually very faint and very small asteroids. They said bust the stadium size, but they're all greater than 10 meters in size. We have no idea what the population of asteroids is that tiny. You know, every now and then one of them goes past the Earth. And if it's a really big one, it's bus size, but most times some of these little ones that go past and give a sort of one-day warning of are really only the size of a few rows of seats in here. The nice thing about the JWST is that because it works in the infrared, it can use the heat signature from these asteroids to give you a rough idea how big they are, so they can estimate the sizes. Some of them were what they call NEOs, near Earth asteroids. They're the ones you have to be most concerned about. With that short observation time, the orbits of these things are not particularly clear. Anyway, when you take a look at the sort of plots of these things here, all of these colored dots in here are the asteroids of 138 that were detected. The green ones at the top, which are all bright ones, they're previously known asteroids. And there's one there that I pointed to with the faint is just an asteroid that was too far off to get a really good measure on the brightness, except that it was lower than what's shown here. And these are all main belt asteroids, meaning they just are in the asteroid belt in the normal position and between on the way up to Mars. And as a result of that, they're not particularly exciting, except that now we know there's a lot more of these things than had expected in the past. There's one Trojan asteroid, that big diamond at the top. That's an asteroid. It's out in Jupiter's orbit. In fact, there's a spacecraft on the Trojan asteroids. Now, when you plot these, this is sort of, you can see it on the left-hand side, it's a number of asteroids greater than a particular diameter. And then you've got the diameter itself. So it's a logarithmic scale. And the asteroids that were discovered are the bottom track, the purple one, but you can see it has a bend in it that starts to go up rather steeply. That bend represents all of these little tiny asteroids that they're discovering. And they're realizing that if you carried on the old trend, the number of small asteroids increased at a certain rate, and until they run out completely or they get so small they cease to be considered as asteroids. But in fact, because that line bends upward, it indicates that the population of these small asteroids is much, much greater than we anticipated in the past. Currently, there's 37,000 plus asteroids as of 2 days ago that are known, and they're coming in, will be coming in fast and furious in thousands once a couple of new telescopes that are being built for launch get into orbit or get into operation. So that little upward trend there, leaving the steady line, is a sign that we're going to have to be looking at these things a little bit more. Perseverance, we don't, or perseverance, depending on how you will pronounce it. Perseverance is, of course, a Mars rover, and it landed in one edge on the basin of Jezero Crater 4 years ago, and has spent a lot of time roaming around. And finally, its goal was actually to climb up to the rim of Jezero Crater and actually get out of it. And after 4 years, it's finally made it to the rim where it can look out across the terrain on other parts of Mars and get into a completely new environment of geology more than anything else that it hadn't encountered before. So this is a picture of Jezero crater, and the little box is approximately where the satellite or the rover landed. And there's a little bit of a gap on the wall there, which is a place where looks like water has flowed in through that gap, and there's a fan here of sediments that were carried. And Jezero has been, or Perseverance has been investigating that fan and the sort of material that's in it. They found that they thought it would be just mostly sedimentary stuff, you know, sand and small gravel that was carried out from whatever river presumably flowed into this basin. But they do find igneous rocks that are volcanic. There was evidence that there was in fact a lake in there at one time, and if you go all up Jezero crater in the internet, you'll find out that more often than not, you'll see a depiction of it full of water. That's more exciting than the real thing, apparently. There were a lot of boulders there, which suggests that the flow, at least at sometimes, was extremely rapid to be able to carry large boulders into this into these deposits. And of course, there must have been multiple ones because they found horizontal layers and sediments in this thing. So this was all pretty routine stuff while it was down in the basin of the crater. Now here's the track that it's taken. As you can see, a little tiny crater there that went around, and but anyway, it's now parked on the left-hand position there at the top of the rim of the crater, and now planning, and now they can see the other side, planning what they can do while they're down there. And so here's a panorama view that it took while it was on the top of that rim, looking out from the crater rim into flat plains and the hills that are off in the distance. And you can't sort of help but get the feeling, you know, except for the fact that there's no trees or any sign of human being, it's like standing on the rim of Riding Mountain there and looking out over the plains. It sort of gives a little more excitement on the things that these craters are, or that these rovers are going to be doing. So it's been mostly ignored for a lot of part of the time because for a while it's just going around picking up rocks. But when you get into this kind of thing, you sort of get a little more excitement about what eventually you put discoveries. Because now it's going to be less looking for signs of life that might have been, or water that might have been, and looking at the actual geology, because this rim and the other side of it is actually stuff that was blasted out from deep layers of Mars and then piled up, where before they were looking at something that's been buried under sediment. So they're going to get a bit of a look at the deeper layers of Mars. But like, all right, so here's some, just a little bit. This lower picture is what the rim looked like when it was in the bottom of the crater right after it landed. So it's actually made its way up that side of that rim to the top of it. When it gets over the hill, it's got a picture or a target already picked out. It's a hill that's got layered outcrops that they can see from satellites. So they want to take a look at the various layers and try to determine what the history was. So the planet that they all have to get on. So I think it could be kind of interesting for the next 6 months or so until we get tired of all this stuff. Too bad it's a little bit too routine. Okay, last thing we'll talk about is Hubble observations. in order to see the tenuous gases that are around galaxies, you can't photograph. They're too faint, they're too tenuous. But what you can do is you can look at a quasar that lies close to another galaxy, and the light that comes from that quasar as it passes through the dust and gas of the galaxy will have certain wavelengths of light subtracted from it, so that you get something like this little graph up here, where you can see the dropouts. Those dropouts represent gases that the light has passed through on the way to being observed by the Hubble telescope. And so what we've been able to do with this observation is, first of all, see this stuff that was previously not very visible, and work out some ideas of how it got there. And what Stach has done is that explosive events in the galaxies like supernovae throw material out of the galaxy into the intergalactic space, but that stuff doesn't go away. It sort of hangs out there and then gradually feeds back into the galaxy, kind of like an explosion that collapses. And so one of the particular elements they were looking for, they've known them for a long time, there's a lot of oxygen in this stuff. Now they've discovered that there's also a lot of carbon in this stuff, which is an interesting conclusion, although oxygen is pretty common in the universe. Carbon itself is not particularly rare, but now we're seeing that there's a lot of it that gathers among these galaxies, which must have been blown out of them over a period of time. And so what you get, there's a picture of M81 or 82 rather. From Hubble, you can see the sort of explosion from the galaxy that may be throwing up this material. So in this pink thing, which I thought was an unusual color for science paper, but this pink thing is shows how the gas comes out of the galaxy in the center. Some of it falls back more directly. Others have actually got certain flows that seem to carry it back into the galaxy. And so that might explain how galaxies that have been around for a while haven't used up all of their material and are still building stars like our own galaxy, because they're having material replenished coming back into the galaxy that was previously lost. So then the question comes with, why does this stop? Why does some galaxies stop producing new stars? So that'll take a little more observation to get that problem solved. Okay, so that's what we've got right now, just a little touch of what's been happening. But if you look to follow what's happening in astronomy or in many of the sciences, I suggest you go to a place called Viz.org, PHYS. You can see their logo at the top, and there's an astronomy and space thing. Other than that, that's the news. Thank you.
All right, folks, we're gonna reconvene at 22 in about 20 minutes. And yeah, so we'll take a short break. Thank you all.
And every PC is unique. Yeah, I mean, every version of the document is unique. Is unique.
Not sure. Good question.
Yes. I know Stan might be. Oh, but doesn't he know that we need to provide it?
Okay. It's okay to go.
Oh, it says Canon on it.
That one does? Yeah, this one does too.
So that's gonna short blue jam. Stand up. See, I sold them. Again, that have a scratch. So. Well, we probably are. Okay, I think yeah, it's got one in the middle. Sure. They turn out that they want he needs to know that. Yeah. I don't. Yeah. But they only work there. Yeah. So know that. I'll tell them that you might have to do it because I think that. Well, I had a house there. I think he doesn't know. I mean, well, I don't know that he can use it. I didn't know. I think 5D Mark 1 but I have yes, yes.
I think it's one of the technical.
Providing there was a time. This looks like someone wanted to fix it.
No, I'll keep
I'm really enough to be
What's it from the game? Yeah. I find that. Jerry, this is my house. This guy. But it's beautiful. I don't think you're and so, yeah, I think it's fine and sleep it. Yeah, we just had. And he said.
Yeah.
Well, folks, we're gonna get started here in a moment. Yeah. If you want for better viewing, maybe move to the right side of the auditorium. Just suggesting, it was suggested that so you'll be able to see better the images up on the screen. So it might be better if you move over to this side of the auditorium. So. Give everybody a moment to move. For those that want. And I won't use time to tell you the joke.
Yeah. Hurry, please, hurry. Oh, sorry.
We're early now. Oh, yeah, we'll turn the light down here then. All right, so, we're gonna get started, for those online, welcome back. I'm going to do my best to do an introduction, so, good evening, everyone. Our guest speaker tonight is Dr. Jayanne English of the University of Manitoba. She'll take us on a wondrous trip with the tidal forces of the universe, combine the light of untold stars to illuminate the forces at work to create gravitationally bound objects of mystery and beauty. Please welcome Dr. Jayanne English.
Okay, so, I seem to have trouble getting on my, there are 3 titles to this talk. But I'd like to start with, how's that? Is that okay?
Okay, perfect.
I'd like to start with my, land acknowledgement. With their treaties, the First Nations and Métis, including the traditional owners of the Treaty 1 lands where I now live and work, generously adopted my Jewish ancestors who are exiled by events in Europe. In the spirit of our aspirations to care for our planet and harmonize its peoples, tikkun olam and reconciliation, I acknowledge and pay my respects to Treaty 1 peoples and their ancestors. Language. I'd also like to thank the RASC for inviting me to give this talk. I'm going to weave together 3 titles. The first one was one that I proposed, which is Visualisation and the Metamorphosis of Galaxies. The second title was what I saw on the website, which was Why Will Galaxies Come in an Infinite Number of Shapes? And the third one was, and what have you been doing since your last talk at the RASC? It's been a long time. I just threw together a little collection of images that I've done over the years. So I'm still making public outreach images. And as one artist said, the astronomers who are doing outreach of this sort are coloring on phenomena. And I'm going to talk later about one in the bottom right-hand corner, which consists of optical and radio data, in which I have assigned colors according to the rotation of the cold gas around the galaxy. If you want to see more images or find out how these images are made, you can go to the WordPress website, so just Google me in WordPress, and you can find videos on how other lectures on how these images are made. Michelle, the pictures look really nice and saturated color on the laptop. I don't know how they're looking, but they're figuring on here. I'm still working with established artists, so it's part of, it seems I'm not only doing art, but outreach at the same time when I do that, because artists bring to you an atypical art audience. You guys are already interested in astronomy, so you come up to see the material on astronomy, but how to get other people interested in astronomy, you could do this by being appealing to atypical audiences. Now, I'm just picking one example here. Emily Gong had a question. Can we analyze the kinematics of autonomous vehicles using astronomy tools and we visualize the results in traditional painting materials? So here I'm using an astronomy tool, a visualization tool. I made a mock data set of an existing autonomous bus that roams around a Chinese campus, university campus. The work was put into a Biennale show in Shenzhen, China, and almost 10,000 people went to see the works in this Biennale. The piece that was made in the end is a huge installation. So here's the installation. very large room size, and Emily has painted the different velocity planes on transparent material. I also make some of my own art, so this is an example that was exhibited in 2023. I converted this from Keynote to PowerPoint, so sometimes the text is going to be funny, I apologize. The image here is piece of work is an installation that did run on my laptop. But it doesn't look like the animations are going to run on Michelle's laptop. And we'll probably have to deal with that a bit later. So what happens here is there's a canvas that's partially unpainted. There's a plane in front to represent the landscape of the Earth's crust. Magnetic field lines are represented by rods. And then there's an iPad that's running. I built a drawing program which allowed me to draw images of data and public out each image. It says next animation here, but I can't get that movie to run. I did just do something. Okay, we'll move on and we'll do it for the other. I can show you guys later if you want. Okay, so I'm doing a lot of scientific visualization. I'll work on anything, even pulsars, Heather. Bit of a tease, because I always swore that I wouldn't work with just unresolved dots. But people are getting me to work on all sorts of new discoveries. This one is an odd radio circle. Have people seen this before? You know what I see? It works. And we don't know what these are. And they were discovered with the ASCAP telescope. This is a combination of ASCAP and NIRCap data. These are the precursors to the next big thing in radio astronomy, which is going to be a huge telescope called the Square Kilometre Array. And it's not going to be in one location. Part of it's going to be in Australia, part of it's going to be in South Africa, like these two precursors are. I also do color maps for specific parameters. So this project is called Cosmos Canvas. It's with Mark Richardson and Dag and your very own Jill Long is part of this. And I'm going to show a bit of that later. And Jill and I also work in virtual reality. For my scientific research, the theme for this talk is going to be galaxy evolution. And it turns out, after you can look back on your career after more than 20 years, you can say, well, my passion has actually been probing the outskirts and halos of galaxies. And in a very weird sort of way, I am now working on galaxies, which I worked on at the beginning of my career, and I'm at the end of my career. And these galaxies are the galaxies of group NGC 3256 and a pair of galaxies NGC 5775 and 5774. So those are going to be in this talk. So the theme for the talk, as I said, is going to be evolution, galaxy evolution, or metamorphosis. But we have to start at what's a galaxy. So a galaxy has a number of components bound together by gravity. Some of the stars, including their planetary systems, there's gas and dust. The gas and dust gets converted into stars. The stars die. Their whole life cycle from birth through to death produces energy. So there's pressure from this energy, pressure from magnetic fields and from the radiation fields. And we also have a large amount of dark matter in galaxies, which we detect by gravitational effects. And it turns out that the galaxies happen to have, I'm going to call three general shapes. The first two are elliptical and disk galaxies. So on the bottom left, that's balls of stars hardly in gas, and the stars are in orbits in different directions. So one star will go this way, another star will go this way, and another star will go that way, etc. So we call that randomized orbits. And the other type, disk galaxies, we call it disk galaxies because they often don't have very strong spiral, so we tend to call them disks instead, and those are flat. So those disks that are flat, we can see them angled at many different angles oriented on the sky. So we can see them face on, like NGC 5774, and edge on, as in 5775. And as was shown before, this is an inverted map in grayscale, and that's because the black, our eyes respond better to the black on white, and that lets us see more detail, more features. We also, back in the day, in the 90s, these are images from my thesis, we saturated the center, you can't see any structure here, we make it very bright so that we can see the faint regions of a galaxy. And these two galaxies, it's interesting because they are actually joined by a bridge, which you could almost see here in this image. And that brings us to another shape, which is what they talked about in the 60s and 70s, is peculiar. So these can be called peculiar galaxies. Another example from my thesis is NGC 3256. And here you can see that's a nice superb example of a peculiar galaxy, and it's got these extensions coming out. We call these tidal tails, you see why. Now these peculiar galaxies can be sorted into different categories, and notice that the representation here for each of the categories is a drawing. It's a drawing of a nearby example of their little category here. So here's NGC 3256 right here. And this was made by the Toomray brothers, Alar and Yuri Toomray, who did wonderful papers back in the 1970s. So let's look at my work on NGC 3256 back in the day. And here's NGC 3256. You can see galaxies are they are peculiar quite well when you look in neutral hydrogen gas. So the red here is an emission line that is observed with radio telescopes. So you're used to looking at H alpha lines. I know a lot of you have an H alpha filter or hydrogen alpha filter, and you have a line at a specific wavelength that you're looking at. Well, in the radio, there's also a specific wavelength for cold hydrogen gas, which is just the atomic form of hydrogen. And so that's what we're looking at here in the red. And the visual is are made with red, green, blue colors. The R is the atomic hydrogen. The green is I-band near infrared, which captures the cool stars. And the blue is the H alpha. And the reason it's done that way is that the lower energies are toward the red end of the spectrum. So the lowest energy emission is colored red, the highest energy emission is assigned colored blue. Now, I was at Mount Strong on the Silent Spring Observatories. I see this package that was really rectangular shape. And I opened it up, and there was a note on top from the director of the Australia Telescope National Facility, where he took the hydrogen observations. And he said, "You can sue us." And that was because the lawyers told me that I could sue them because they took an image from my thesis without asking me if they could. And they produced a postcard with it. That was a stack of postcards. They also made a Christmas card out of it. You might like looking at this now, it's pretty awkward, doesn't it? So why would they use this very awkward picture to promote public outreach of galaxies? And that's because all the other images of hydrogen gas at the time are these contour lines. So awful rainbow color map here for the optical, which is very unrealistic. And then the each of these contour lines is an intensity, and different intensity, the brighter intensity is more towards the center. And the public can't understand contour lines, so it seemed like language was much more comprehensible to the public. So why are we interested in these filters and these telescopes? Well, for the neutral hydrogen gas, the gas temperatures are like tens of degrees Kelvin to 100 degrees Kelvin. And this cold gas is going to, if circumstances are right, be collapsing and forming into stars. That's the fuel for star formation. If we look at the infrared band, there's not much dust obscuration and you can see stars. They're cool stars, they're typically older and smaller than our sun, but it gives you the structure of the disk of a galaxy. And then if we look at the H alpha, then we're looking at the heated ionized gas, and that gas is heated by stars that are younger than 10 megayears. And actually, in any area where there's ionized hydrogen, the mean age of stars is 3 megayears. And if you were to look, say, in ultraviolet, where there's the hotter stars, even that population is polluted with stars at the age of 100 megayears. So we say that when we're looking at H alpha, we're looking at stars being born now. So it's looking at the stars that we can look at. Regions where that have the youngest stars. So we could say, in terms of galaxy evolution, this is important because the hydrogen gas is going to be converted into those stars that are forming. Well, what can trigger hydrogen gas to be converted into stars? Anybody want to shout out some reasons? What could make you have a cloud sitting there in equilibrium, what could cause that cloud to collapse and form a star? Any ideas? Shock waves. The galaxy. Collisions of what?
Massive gas.
With another bunch of gas. And what can gas? So what can cause collisions of gas?
Other galaxies.
Okay, so we're getting somewhere here. Okay. So I'm not gonna these, I'm just gonna say, okay, keep your eyes out for these ideas as I get through the talk. And another question is, what features can we look at in galaxies that will tell us, oops, oh, I have to be careful with this wheel, sorry. That will indicate physical causes of change within galaxies, causing them to metamorph. Okay, so let's go through what can happen. One of the things we can study in galaxies is the star formation rate. So the star formation rate is how many stars are going to be born per year, and we can use H alpha to do that. This is NGC 5775, and I've used Hubble Space Telescope data for this one. It looks quite different than my thesis version, just quite a big change. And we can compare the numbers that are forming now with the existing numbers of stars that we see with broadband filters. By the way, what do you guys call the emission? I don't know what the profession is called, but what do the citizen scientists call the filters that are wide? Broadband, you call them broadband, good. Okay, so broadband or wideband filters. So we can count up the existing number of stars in a broadband filter. And so the galaxy will count as a change when the number of stars change in the galaxy. Okay, when it increases its number of stars, for example. And there's a negative at that. And so the stars are going to form out of gas, and I have an example of what the gas looks like using, again, the radio telescope in Canada. And this is from the disk of our own Milky Way galaxy. And the colors here represent the velocity of the gas, the hydrogen gas, the neutral cold gas as it's moving towards you. It's the bluer and it's warm golden as it's moving away from you, and the bluer is coming towards you. Okay, so there's a lot of material here that stars can form out of. And we just looked at the optical version of this galaxy. We're going to look at what's invisible. We're going to use a radio telescope. And can you see up on the screen? Yeah, the change there?
Yeah.
Okay, so this is from the VLA, it's an NRA observatory, so National Radio Astronomical Observatory Telescope. And what we're looking at here is radio continuum emission. So radio continuum is the same as saying broadband, but in the radio red region of the electromagnetic spectrum. Now, what causes this emission is the electrons are on a curved trajectory, and they can be put on this curved trajectory by either being in a plasma, a heated gas, and an electron sees a proton and swings around it. So that's thermal. That's a thermal mechanism. Or it can happen because the electron is moving in the curved trajectory because it's spiraling around a magnetic field line. So those are our two mechanisms. Okay. There's a project called Changes, which looked at 35 different galaxies looking at their radio continuum emission. I've used still here NGC 5775 to give you the diameter of a galaxy. In our sample, we matched all the halos up in size from 30 of the galaxies and we stacked them together. This reduces the noise in the data and it increases the signal. So this way, when we're looking at things that are faint and we stack them together, then we can see what the typical shape of a radio continuum halo is. Okay, so this indicates that this radio halo indicates that there are magnetic fields in galaxies, that they exist. So how do we know that there are magnetic fields in galaxies? When we look at the radio spectrum, we can figure this out. It's analogous to looking at an optical spectrum, and probably you know something about optical spectra, so I'm going to start there. So say you want to know what the temperature of a star is. Your spectrum goes in wavelength, increasing wavelength size from the left to the right here. That's your spectrum, and the y-axis is intensity. So the brightness, this is a kind of peak, and the star emits light at every wavelength, so it creates this distribution. And you can look at a cool star, and its peak is shifted to longer wavelengths, which is redder. And you can see that you can measure the slope in the tail over here. Oh, I've been pointing at things and you haven't been seeing them. But there's the red line there on the slope of that star. And for the very hot star, that's star A, the peak is shifted to the other side towards the blue, and its slope is steeper. So we have a flat slope for cool stars and a steep slope for hot stars. And we call the flatness parameter here a color index. We're working the optical, we have colors. How many people have seen this before? Okay, that's new. Okay, we do the same thing in the radio. We do it for a galaxy. This is the distribution of the spectrum here in radio continuum. And what we have, that dark line. I'm just still trying to find how people did a pointer before, but I'll just have to jump up and try and reach this. But you can see if you have a plasma, which is from an ionized gas and it's thermal, what you're going to have is a flat slope, right? And if you're going to have magnetic field lines, it's not thermal, and we have a special name for that kind of radiation, it's synchrotron. You see, it's got a steep slope, right? So we have flat and we have steep. So if we're looking at a galaxy that has a really steep slope like that, then we know we have magnetic fields. And, oh, great, there's a pointer. Okay, so now we have a steep slope and a flat slope. Now, just like the color index, where we used one number to parameterize the flatness, that meant that you can use one number as well to parameterize the steepness and flatness in the radio range of the spectrum. So what I want to do is figure out a visual way to represent this. And I'm going to show you the color map for that. So first thing here is we have a handy dandy little tool called a color wheel. And on the color wheel, the colors, so I'm going to want color maps and show the spectral index. So we don't have colors, so we have to call it spectral index instead of color index. So we have a color wheel here that I'm going to use for representing the spectral index values. Across on the color wheel, there are colors. If you stare at one of them, you will see the other color when you look at a blank white page. Those are called complementary colors. And oh, there it is, good. Complementary colors. So I'm going to pick orange and cyan here as complementary colors. And then something else we have on the color wheel is an analogous harmony. And all that means is that the colors are beside each other on the color wheel. So this orange, then a light orange, a yellowy orange, and a yellow. That makes an analogous harmony. Our eyes like to see these things, right? So we can work with our eye-brain system. Now, where are you going to say, now it's flat and now it's steep for the slope? So you look at the physics and you put the parameter number that matches up with the physics. We say that something is flat at a particular threshold. And I'm going to color that dark cyan. So I'm going to color it this color in here, dark cyan. And anything that is even more flat is going to go towards purple. So that's analogous, dark cyan through to purples. And then anything that's steep, we got a number for that. And we're going to assign that the complementary color of orange. So that's over here, and then go from orange through to yellow. And that gives me a set of colors that the eye-brain system likes. And that's going to represent where there are steep spectral indices. And then I'm going to mix colors together in the middle. And so when I do that, I can make maps like this. So this is called scientific visualization versus information visualization, which is more like graphs. And what we can see right away when we look at this galaxy here is it's purple in the middle. And it turns out at the radio wavelengths that we're looking at, if there's a black hole, it's going to have a very flat spectral index, the emission in the region around the black hole. So we can look at this right away and say, oh, that galaxy has an active galactic nucleus. And then here we can look at our edge-on galaxy, and we can see that right in the middle of the disk, where all that hydrogen gas is, it's really flat. Where the stars are forming, it's flat because it's thermal. It's ionized plasma that's there. But if we look towards the halo of the galaxy, it becomes steeper and steeper, and that steep spectral index happens when you have magnetic fields. Ta-da, we have magnetic fields. I'd like to point out that we have a project on GitHub. It's Cosmos Canvas, and Jill is part of this as well. So we have to work on this map. This has a whoops. Okay, let's go back. Okay, now I want to talk to like really proving there are magnetic fields here, and radio antennas are really great because they can detect actually polarized emission. So let's all pretend we are making a wave of light. Okay, a light wave. A light wave consists of an electric field. That's going to be that finger, right? 90 degrees to it, we have a magnetic field, which is that finger. And the wave of light is going to come towards you like this. Anybody want to do that? Yeah, everyone want to make a light wave? Okay, so your light wave, your magnetic component of your light wave is going to be aligned with the magnetic field in the galaxy. If you have a bunch of these lined up like this, that's called polarized light because they're all aligned. They don't have to be all aligned this way. They can be this way, or that way, right? That's called the polarization angle. And we can measure that with radio telescopes. And what we do is we take a bunch of those polarization lines and we collapse them into a vector on a map that shows us where the polarized light is and the direction of the magnetic field line in the galaxy. How do we look at that for our papers? It looks like this. So there's our little vectors, but the public doesn't like little vectors, right? And there's our contour lines, which they don't like. So if we're going to use make a public outreach image, we have to do something else. So what we do is we convert these vectors into flow lines. And we use an algorithm that's called line integral convolution. And it's kind of like if you have a beach, lots of sand, you drag a stick through the sand. So what we do in a computer is we throw down a lot of noise to act like the sand in the beach. And then we trace our vectors and make flow lines. And the images you make that, like that. This is by Jayanne English. And then this is what I did for NGC 5775. Okay, this is an example of my first mode of metamorphosis. This mode is called secular. Anybody who does comments might know that that's a historic word for a particular kind of periodic orbits that you never thought were a period. And what it really means is it's this very slow evolution. So this is an example of slow evolution. We don't know how magnetic fields change the shape of galaxies, how they affect the star formation rate, but that's ongoing research. But if it does have an effect, it's going to be slow. Another example are bar instabilities. So when you have a bar, the gas flows to the center of the bar and accumulates here. And then Judy's right, gas clouds clump into gas clouds, and that will cause them to collapse and form stars. And here's the JWST image showing the regions of star formation. So we're going to take the gas and deplete it by converting it into stars and creating more stars so that it's a change in galaxies. Then there can be these fountains, thanks Jay for your talk earlier and showing this galaxy. You can have fountains. So let's get all that gas happening into the center of the galaxy. And what's going to happen is you're going to form a lot of stars, the young hot stars, all the stars actually, but the young hot stars are going to have really powerful winds coming off of them. And if you've got lots and lots of stars, you've got really powerful, like a whole cohort of stars creating one massive wind in the center. And that's going to give you outflows from the galaxy. And here you have the dust coming out of the galaxy in the infrared, and then the hot kind of really hot gas, million-degree gas in the blue in X-ray. And so now what you're doing is you're quenching the star formation because you're removing all that gas from the galaxy. And there's no fuel, so the star formation inside the galaxy disk is going to slow down. Oh, you can have smaller versions of this. Little ones dotted throughout the disk of a galaxy. Those are called chimneys. So chimneys can be pumping material up into the halos as well. And then, of course, you can have active galactic nuclei. And active galactic nuclei, some of the gas is falling onto the center, onto a black hole. And not all of the gas goes into the black hole because of its own magnetic fields. The gas will come flying out in the form of jets. And there you go, you have submillimeter in orange, and you have hot X-ray gas in the blue. Now, all of these things look really dramatic, right? The ones that I've shown you, but actually they're very slow, which means it takes less than that. The changes in the galaxy takes more than 1 billion years to happen. So now we're going to look at nut centers A, and Now we're going to look at different mode. Where it happens fast. So I showed you that categorization by the two Ray brothers earlier. And it actually turns out that these are sequence for colliding galaxies, interacting and merging galaxies. So we can start here, go through all these different stages and end up here. Now, how do we know that? Okay. Say you go to a shopping mall and you take a bunch of pictures everywhere. You'll see grandparents, you'll see babies, you'll see teenagers, you'll see an awful lot of adults. And you can build up from that the evolution of babies into grandparents, right? In the same way we look at the sky, we take a lot of images of these different peculiar galaxies, we throw them into a computer along with all the laws of physics that we know, and we get a time evolution sequence. This is called hierarchical formation. It's fast evolution because it's taking smaller components and putting them together to form bigger components. So these are the poster children for representing each of these stages. There's lots of galaxies that look like this. Okay, Michelle, I hope this works. How do I get this to work? I'm moving forward. If it doesn't, I'm gonna have to do galaxy dance. Oh, what are you doing? Okay, this is happening up there, even though it's not happening down here. Oh, how are you getting that? Like, okay, Michelle, keep doing it. Oh, it's going really slowly. Okay, so this is one of my, this is like from back in the 90s, 80s and 90s, this example, which is going slower than it usually goes. But we have two equal sized galaxies. That's why it's called major mergers. For this case, this is by John Kavinsky. And you can see these, what happens, what's set up in the material is tides are set up in the galaxy's material, the same way that the moon sets up tides in the water on the earth. So we call these things tidal tails. And the gas starts to flow into the center of the galaxies, right? So you're going to get gas flowing in the center, star formation happening in the center. And you see this bridge that forms between the two of the galaxies. And they're going to be in orbit together, and then they're going to merge together. And this is going to go really, really slowly. So I'll just keep talking about the next part, which is in order to have this actually happen, they didn't think that it happened in the 70s. They didn't know about dark matter. And they thought that the galaxies would just pass each other by, so there wasn't strong enough gravitational pull. But then they discovered dark matter, and it's like, 90% of the galaxy's mass is in dark matter. It's a lot more than what you see in stars. And so that meant there's enough mass because of the gravitational attraction, and the galaxies can then orbit around each other and finally merge together. You get a common envelope, then the cores of the galaxies merge together. And all of this tidal debris, you get stars going this way, you get stars going that way, you get stars going the other way. The thing that's in space that is close, that has a gravitational pull, is the center of this galaxy. So all of this tidal debris will fall back onto the galaxy. And this happens fast. It happens in about 500 megayears. So we want to figure out something about how do we know that there's dark matter? We know from the velocity of the galaxies. Galaxies are rotating. We know what we can use that to figure out how much dark matter is. So the velocities are a very important parameter. So we wanted to build a color map for velocity, and your projector sucks. So sorry about this. If you want to look later, I can show you what's really supposed to happen. But again, we have the analogous harmonies, but what we're going to concentrate on here are complements across from each other on the color wheel. So we have this more red, and more red-orange here, and we have this kind of greeny turquoise here. We're going to set them up for a map here And you have, if you mix colors together correctly, you get white or neutral gray. We call that harmonious. It's not a value judgment. It's just an art label for it. But here I put the greeny blue, the darker red here. I take a little bit of the red and I mix it in with the green and I'll get a color beside it. Take a little bit of green, mix it in with the red, I get the color beside it. And if it all mixes together correctly, which it does on my laptop, you get a neutral gray in here. Okay, so you can build, that's how I mix colors together in the spectral index mapping. And we use this one's called compensating tones color scheme. Now, we're going to be looking at how a galaxy rotates to figure out how much dark matter there is. So now I have to do galaxy dance. So one of galaxy, galaxy dance. So for the Doppler effect, you all know as a car goes by, as a car goes by, there's, right? So coming towards you, it's got a high pitch, right? And going away, it's got a little bit, same thing happens in light. It has to be coming towards you. It's along your line of sight that you're measuring things so that they're going away from you, they're going towards you along the line of sight, but the same thing happens. Now the high pitch is high frequency, which is short wavelengths. Short wavelengths are to which end of the spectrum? Blue or red? Blue. And then going away, red. So we have a red shift and a blue shift, right? Okay, so I'm a galaxy. And this is going to be gray because this is going towards or away from me, right? And I got to rotate. This hand is going to be blue, and this hand's red. Okay, so if I have something that goes from blue through those compensating tones to red, I have the signature of rotation, right? Or velocity. Okay. How did we use to represent redshift and blue shift? Color, this is NGC 3256 again, we colored anything that was redshifting, fire engine red, ultimately blue for going away. So visually, which color is popping towards you? Red. Physically, what should be happening to that red? It should be going away. Okay. So we weren't working with our grain system. We weren't using our grain system to go with what we wanted to say, but we could actually do an approach that supports intended B using perceptual effects, working with our grain system. There's our compensating tones, color mapping. Look at that, the blue's coming forward, the red is going back, okay? And so this is NGC 3256. You have not seen this, it's unpublished yet, it's new NEARCAT data. But now look at this fragment of gas, you can really tell that's flying towards you, right? Okay. And this one is NGC 5775, and you can see the compensating tones color map, so we've got the signature of rotation. Look at this beautiful bridge, H1. Then you can see that 5774 is space on, doesn't have any line of sight losses. Oh, there's something nifty you can do with this. You can take this color map and you can make every intensity in the color map the same. Different colors, the same intensity. You convert this to grayscale, it will be one solid gray blob, all the same color gray. And I'm going to do that because I want to add it to an image that is grayscale. And I don't want to impact the grayscale image. I don't want to make bright parts darker and dark parts lighter. So I make it all one value. And then I add in the grayscale image. And now I can see how that galaxy is rotating. Again, both the disk and all of this is actually optical ionized emission. So it's extending away into the atmosphere of that galaxy, and that material is also rotating. Okay, so let's go quickly through some pretty pictures of the hierarchical fast evolution. One of the first stages is two galaxies coming together like the antennae. The other companion galaxy to this one is out of the field of view, but star clusters are forming here. One of the things that we can study to let us know about evolution, lots of stars, gases being consumed into forming stars. They're making clusters of million stars each in this tidal debris. So it's young globular clusters, but instead of being 10 billion years old, these are really young 10 million year old ones. I have to rename this image, don't I? I'm going to say yes. Okay. And then finally, it's going to end up with in this sequence into this kind of mess here, but all of this tidal debris will fall back towards the gravitational center and end up making an elliptical galaxy, nifty elliptical galaxy. We can see the jet from the black hole here. So gas is flowing. What little gas is left, there's some of it flowing into the center and creating these jets. You don't have to have equal-sized galaxies for this to happen. You can have galaxies of different sizes. We call it minor mergers if they're 10 the size of the bigger galaxy. We can have groups of galaxies merging together. This will all form one kind of galaxy. This little group of galaxies here, we can see the star formation happening. And where it's blue, that's where there are young stars that have blown away their gas. And this diameter here is about the diameter of our Milky Way galaxy. So these are small little dwarf galaxies that are going to collect together into a galaxy. This transition from being little galaxies to becoming larger galaxies is very fast. So we don't usually see, so we will see many more galaxies in the elliptical phase and in the disk phase than we will see the peculiar galaxies. Now, there are other modes for, well, I think I would actually include the next one I'm going to talk about under hierarchical as well, but there are other modes for forming galaxies. And one of them that I'm going to talk about now is using the structures in the universe as a whole. So if we look from the telescope outwards in redshift, we can see these structures here. So these are galaxies all forming these structures. So it's not like they're distributed like grains of sand on a beach, but they actually form the large scale structure of the universe, which looks like a web. So when we talk about it to the public, we always call it cosmic web. And if you can put together a computer program and start off with fluctuations from the cosmic microwave background, you get a cosmic web, right? Now, here, there's little yellow dots, and that's where galaxies will be situated. The rest of this black is all dark matter, and you can have gas flowing along these dark matter filaments. And they can help explain galaxies like this one. So galaxies like this one, you have one galaxy surrounded by a ring. You used to think they were rings. It looks more like a disk, doesn't it? By rings of stars or disks of stars. And then we would discover these in the optical, and then we'd take out our radio telescopes and we would go and find gas in these rings. But something really exciting has happened. And we have a new discovery, which is that you can look and survey hydrogen gas and discover polar ring galaxies that can be explained by gas flowing along the cosmic web to form them. So here's a galaxy. This was discovered in hydrogen gas in the ASCAP telescope in Australia. And the bluer side is blue shifting toward you, and the warmer color is going away from you. So that is telling you that this gas is rotating, orbiting around that galaxy. So we're going to find many more polar rings. Now, you can form a polar ring using interactions and mergers, but the scenario I like is this one. And do I need your magic game? Oh, no. Sorry, this arrow here. Oh, that arrow. Okay. Note in this simulation, it's going to be the gas and dark matter. Yay, thanks, Michelle. And you're going to notice interactions and mergers, like right there, hierarchical, smaller bits coming together to form bigger things. And so we get a galaxy forming here, right? And gas flowing along a filament to come back in. And you think that you're going to get a polar ring starting here. And then what happens is, oh no, it's going to be a merger. Going to collapse in together. And notice, because gas is flowing in from filaments, you don't get an elliptical. You get a spiral. So you can make big spirals that way. And then what's going to happen as this goes along, we're actually going to get gas flowing in from a filament and forming a polar ring. And there we go. There's a polar ring galaxy. What do you think? Like the scenario?
Yeah.
Okay. Okay, so I still have some more to say, but I'm going to take a little break from my slides and go through a summary. It seems like a good point to do it, and add a few reflections. So by looking at all these observations, you probably noticed that when we went through all the different regions of the electromagnetic spectrum, that galaxies aren't simple objects, but they have complex structures. And galaxies aren't static, but that they change with time. And those changes can be slow, and those slow changes could be due to magnetic fields, bars, fountains, chimneys, black holes, and jets. And what's going to happen, it's going to change the number of stars in the galaxy, if not the shape. And then you can have fast changes, which are hierarchical changes, interactions and mergers, and it can be more than pairs, it can be groups of galaxies. And that's going to change the shape of galaxies, even making a new kind of galaxy, going from spiral to elliptical. So you can ask a question here, do fast changes trigger the slow changes? Well, yes, because they're going to cause the flow of gas to go to the center and create those fountains and those black holes. Okay? Gas falling on black hole and jets. Okay, so the shape of galaxies aren't arbitrary, but they result from physical processes. So one might think that because you have an infinite number of galaxies, you can have, well, it's not an infinite number, but hundreds of thousands of galaxies, you would have a different shape for every galaxy. Anything would be possible. But anything is not possible. These shapes are governed by the galaxy evolution processes. And by tracing the shapes, we grow to understand what those processes are. On top of that, galaxies are the habitats of stars, and those stars have planets, and we know of at least one planet with life. So if we're studying galaxies, we're studying the habitats of life, and where life can potentially arise in a galaxy. Additionally, we use galaxies as test particles in our simulations for cosmology. So we have to understand galaxy evolution and decouple that from the hypotheses we're making about the future of our universe. It's going to happen to as time goes on, the universe as a whole. Now, a lot of you have probably been waiting with bated breath about the you part of my talk, and that is going to take us back to the galaxies that I've been coming back to at the end of my career, from the beginning of my career, to study. NGC 5775 is part of a sample of 35 galaxies in a radio continuum study that uses the VLA in New Mexico. And we collected that sample together, just saying we need the galaxy to have enough radio emission that we can detect it with the VLA, and it has to fit within the field of view. So we thought that we were going to have a sample that had isolated galaxies and only a few interacting galaxies. Well, and galaxies that weren't in gravitational environments like groups. But what we discovered was there's really only 2 isolated galaxies. And what we would like to have is more optical observations on these galaxies to know if that's actually true, that they are really not affected or perturbed by anything, whether it's the secular evolution or the fast hierarchical evolution. Also, this is actually really well done by Adam Block, but this is an example of really challenging observations in the optical. This star here really can be totally saturated and hide the galaxy. You kind of need to have a little disk in front of your camera in order to block the light from the star, because one of my colleagues swears that there's tidal debris out here, and we really can't tell because of the starlight from that star in the foreground. So there's some challenging observations that can be done for the changes sample. But what's really important to us now are observations in the southern hemisphere where there's ASCAP and meerkats in South Africa. Here's our Juliana Saponara said, yes, please show my data to you. Notice that this radio continuum data does not need any contour lines to show you features in it. We've come a long way. Very sensitive data. Adam Block did a really nice optical imaging of this galaxy. And in our continuum data, we also have these little galaxies here. But in the group for the NGC 3256 group, there are only two well-studied galaxies. This one, NGC 3261, and NGC 3256 itself. But this group has 10 galaxies in it. And this is only part of the group image back again for my thesis and subsequent papers. Here's NGC 3256. 3263 has a long tidal arm. So the red is the neutral hydrogen gas, long tidal arm here. And this happens in a computer simulation when you throw, so you have the galaxy disk like this, and you throw a dwarf galaxy orbiting like this, it'll shoot out a nice long tail. We don't know which of these galaxies is the dwarf that's causing this tail to occur. And look at this. There's a cloud here, just hydrogen gas. This is the same amount of gas that's generally in a galaxy. This is our new meerkat observations velocity field. So 3261 is down here. And you can see that there's a lot more clumps of blobs over here in the cloud. And we've discovered many new little H1 dwarf galaxies. And some of them in the survey data that we have, general survey data that you can get online, there might be galaxies inside them. But we really would like more exposures, longer exposures, because the survey images are short exposures. They can't detect if some of these dwarfs have stars. They can't detect if the clumps in the cloud have stars, and they can't detect. Okay, so I showed you fountains, right? So if you have a fountain that blows gas out of the galaxy, if that gas will have no stars in it. But if it's tidal debris, it will have stars in it. And so we want to see if there are stars and bridges and filaments, stuff like that. See if it's tidal debris or gas that's blown out or anything else. Oh, sadly, there are no H alpha observations. And I've actually asked observatories if they could do it, and they've all moved on to spectra and they're not making images. So we can't trace the locations of where the youngest stars are forming. So these would be very challenging observations to do, but I was just being shown those images from Curacao, right? And so maybe that sort of observation could be done. So I hope some of this will be of interest to citizen scientists. And Juliana has two more groups of galaxies for you to observe, besides NGC 3256. Okay, and if you don't want to do observations and your jam is playing with computer programs, we're refining our line integral convolution algorithm and making some work there. So just to quickly finish up, I have three titles: Visualization and the Metamorphosis of Galaxies. Why do galaxies come in an infinite number of shapes? And what have you been doing since your last RASC talk? Okay, so I hope I piqued your interest. in observing galaxies. Visualization, well, that's really advanced significantly from my thesis days. We are using observation and visual analysis with perception-based color tables to illuminate all the processes like star formation, locations, black holes, halos, magnetic fields, gravitation interactions, and so on, which give us the processes that change galaxies, cause the metamorphosis of galaxies. And they can change these collections of stars, gravitational amount, stars, gas, dust, dark matter, and create galaxies even of different shapes. Why are there a finite number of shapes? Well, because they're limited to the morphologies that are produced by slow, fast evolutionary scenarios. And the observations help us sort out what these scenarios are. And what have I been doing? Oh, it's a whole long list. So I've gone back to my early investigations of peculiar galaxies. I'm doing visualization in a variety of forms, including virtual reality. This is a picture of me yesterday, and Jill and I were working on this before we came here tonight. For many projects, I've been doing public outreach, and that includes collaborating with artists. And in other words, I'm doing too much, and there's more to come. I hope you will join us in these investigations. Thank you.
Thank you, Jayanne. Do we have any questions?
That's good.
Irregular galaxies fit in the scheme. Are they small or independent, or are they just distorted?
So the irregular category of galaxies was based on optical wave alpha, for example, in young stars. So the poster child for that was the large magnetic cloud. But way back in the day, like the 60s, folklore took images along with penetrating in the optical, and it's based on this galaxy. So it's kind of a misnomer called irregular, but there are lots of irregular galaxies. When you look at them in the infrared, that irregularity is only like tracing the star forming areas. So, yeah, but it's still a valid, it's still a category that's used. Yeah.
This is a totally off the wall. I have no idea if it's 90 or I'm not catching it. You mentioned fairly close to the start that magnetic field lines.
Yeah.
We're interested in how they affected stars.
Yeah.
Formation of stars. But stars also have magnetic fields. Okay. And how do you separate that when the data are or the fields around the stars are too tiny?
Yeah, the fields of the stars are too tiny to be involved with. The scales are like the stars are unresolved point sources, and the magnetic field observations we're doing are about 11 second resolution. That's really good right now. But that's very large, and the relationship between the stars and the magnetic fields is, so there's the main scenario that's used now is that it's the stars and the star formation rate that is the association with magnetic fields. So the stars form, when you have a cluster of stars forming, the more massive ones are going to explode as supernovae. And when that happens, the galaxy itself has an internal magnetic field in the galaxy, and that the electrons in the magnetic fields are entwined together. So when the star explodes, that plasma is leaving the distant galaxy, drags the magnetic field lines with it and up into the halo. But there's another one which is part of the instabilities, and I would like to know as part of like the tidal things, we'll be looking at the tidal debris, we need to see if we could get sensitive enough information on the main tidal debris, the bridges, for example, this continuing emission there. Is that due to thermalized gas or is that due to magnetic field lines? Does the interaction of galaxies pull out magnetic field lines as well? I'd like to know that. So, and the other thing is the changes program is really looking for the origin of magnetic fields. So the rotation of galaxies, convert that kinetic energy into energy in a magnetic field. Like the sun has its magnetic field, which stars like you mentioned have magnetic fields in the air. That's because of the electrons moving, creating a current that creates a magnetic field. Galaxy gas, electrons moving, creating a current, creates a magnetic field. Or did the magnetic field, does the universe come with a magnetic field and then for everything like galaxies and the universe end up having a
Yeah.
So I asked the flip side of the question, I said my radiant chemical. So I think what you did with the color wheel to represent red and blue with the aqua and the red color. It's quite brilliant actually, because it's so obvious and yet it took a long time, 50 to 60 years. So do you also collaborate with neuroscientists who are interested in much part of the visual system, text work, and or complementary colors managed in the same place at some level of the visual pathway? Like that's the part I grew up with.
Yeah.
I didn't grow up with what you do. So I'd be very interested in understanding if you can feed information like to neuroscientists by giving that talk. They might be really interested.
Oh, I think they probably already know about it because, this has been known by artists for a long, long time, right? This is the color wheel that, yeah, but artists have known this for centuries. So what I do is I take what artists have, because they've been practicing it for centuries very successfully, and I take what they have been doing with it, and put it into my work, right? And when I go to look at neuroscientists, or even Colin Ware is I think he's in the Department of Psychology, but it's engineering and psychology and certain information, they're both called information visualization. And he also went to art school. So he started off in something like physics or astro and went to art school and then went back into like engineering and psychology. So I had a psychologist know about this, and I often look for references to the art information for the color theory courses in psychology books, but it's part of the new program. It would be interesting if you did find a neuroscientist to work with us, for the VR stuff, right? I think that's where it would be really important, because I have no idea, like, I haven't been an artist working in two-dimensional color space, right? Except for a few, one of them, if you go around campus, you'll see these color 3D sculptures in color. Bernstein, that would be, you can see, oh no, Bornstein. And he's, but hardly anybody does that. I know another guy about me. So, and architects. But otherwise it's frontier work. That's what I'm trying to get to. Sorry about that being discursive, but it's so frontier work. I think that's now where we need to bring in the neuroscientists. But the thing that I did with the color wheel is actually first year art college. So,
But it wasn't never in the visual.
No, it wasn't. And I brought that up in a talk. I was at a small conference, and when I was a graduate student, and I said, the rest going, the rest is going for the views or that. And everybody went. And then, yeah, so it seemed that nobody was interested in dealing with that. It seemed somebody who actually cared about that. But the landscape has changed and everybody's really interested in visualization. You had a legend beside your thing, everybody was smart enough to read the legend and understand it. There was no massive public outreach where you had to say things out of glance. So as time went on, that landscape changed, and now all astronomers, almost all astronomers are really interested in visualization. And it's got a name, visualization, right? Oh, yes.
Is there any in your work, which correlate with the two globular clusters as well? We never looked at globular.
That was part of my thesis.
Okay.
It was about globular clusters forming an interacting galaxy.
Okay.
So, yes, so, we do look at globular clusters. Not much color in a globular cluster, but there is, you can make velocity field map. You have to use globular clusters to look at dark matter and elliptical galaxies. Did you have a specific question about it?
Just if you could draw conclusions from the nature of globular clusters, the research you've done now.
Yeah, so, all galaxies have globular clusters, even if it's a dwarf galaxy, it will have these globular clusters. So, if you're going to develop a theory, scenario or hypothesis about how galaxies form, then you have to build globular clusters in that theory. So it's kind of constrained. It's kind of like human beings having belly buttons. Like all globular clusters, belly buttons in galaxies. But thanks for that question.
Well, again, thank you very much, Jan. In particular, I just want to mention that for years, that blue shift, red shift, I've always understood it, but it always bothered me. And then tonight, with that one slight color shade change, everything came together. So visualization, I guess, terminology that's used, it's incredible what it can do for us. So again, thank you again, Jan, on behalf of the RASC Winnipeg. Thank you. And of course, everyone's welcome to join us over at Boston Pizza on Pembina, and wish you all a happy new year and safe travels home. Good night.
Steve can go there, but okay. Was there when I got there?
Okay. All right. By any chance, if somebody lose their takeout card for the bus? It'll be at the bus card. It'll be up front here. Yeah.
Oh, yes.
Thank you. Managed to get to work.
Running Zoom, I'll see, right?
Yeah.
Yeah, so I'm gonna brand it on there.
Yeah, well, yes, so, yeah.
Yeah.
Hello,
Is James Fast here?
yes, James. This lady's looking for you? Ah, you should have put the two together.
I've gotten 2 emails from him since I joined the group.
Oh, yeah. Excellent.
Can go tomorrow to Gundy,
Yep.
but if it's going to turn into a blizzard.
No, I get that. Yeah.
Because I'm about as far north of the city as Gundy is south of the city. So
Yep.
I took about an hour
Yeah. Okay.
and I've sworn off driving home with blizzards.
Yes. No, I don't blame you. Where James? Oh, James just got caught there. He'll be here in a second. He's in the orange jacket with the gray top. Thank you.